Okay, looks like we can start early. I'm actually stepping in for Stuart Yoder, who was supposed to be the speaker, but you may have noticed that it has changed. He couldn't make it to this conference. So I'm stepping in, and I'm going to be presenting with Zach from AMI. I'm Don Wei from ARM. So what we are trying to do here is to talk about the secure system boot on ARM. And for that to happen, we would like to have, certainly the chain of trust, and it's going to be established from the immutable ROT, right, the root of trust. And we would like to have secure I/O configuration at the boot time. And we also want the boot flow to be platform specific, because we want to allow for flexibility and innovations across our ARM ecosystem. And so we want to also make sure that the ecosystem is collaborating and to enable a lot of the proven designs and technologies. So the thing that we are wanting to have is a secure boot with a platform active root of trust, PA-RoT. I was just chatting with Zach before the show here. The last session was about the PRoT. I think I was like a little confused about the terminology. It looks like the OCP is settling down on the PA-RoT terminology. So these two things are very much the same. So PA-RoT provides the capabilities of authenticating the I/O devices, the BMC firmware, and it also protect and manage the firmware store, the RTU. And also, I think you may have participated in some of the sessions that we talk about on the ARM ecosystem. Because we want to establish the interoperabilities for the system manageability, right? We actually have defined a specification called Server Base Manageability Requirements, SBMR. The SBMR basically, as you can see from the chart over there, we're trying to define the base interoperability and the commonality for how the BMC interacts with the server SoC, how the BMC interacts with the the different controllers and I/O in the platform, and how the users are interacting with the platform. So we are trying to establish the kind of the baseline foundation. And it enables the subsystem interoperability. It specifies the manageability design for the ARM ecosystems, trying to be as common as any other server systems that you have been seeing, right? The same kind of interfaces as much as possible. So it's a collection of design guides and rules and to just ensure that no matter which server system you're procuring, they offer at least the baseline interfaces that we can all use. And the use cases also cover, not only the manageability, but also the security side. We do have, the ECR stands for the engineering change request. So, we have set of the earlier versions of a spec already, but now we also have the approved ECR that documents how this specification covers the PA-RoT. So the security use cases that are supported by the SBMR spec, the PA-RoT measures and authenticates devices, including the BMC, right? And we support the device attestation. It can be performed at a configuration change, update, or the platform reset. There's also the support for the Redfish out-of-band commands. It presents the firmware measurement externally, or for the audit and collection. PA-RoT actually acts as the RTU to ensure the authenticated images are committed to the firmware store, and it actively monitors the firmware store integrity as well. So with that, I'd like to hand over to Zach to continue the presentations that we have been collaborating with AMI.
Sure. So this isn't going to be too complicated, but I'll try to hit the key points for you all. So this is for device attestation, as we've talked about before. So you'd expect, to an extent, that the PA-RoT has already done some base validation of maybe the BIOS, the BMC, or some of those base firmwares on the platform. And now you've got some plug-in cards that are plugged into PCI slots or PCI Express slots and also soldered down on the platform. So this follows a flow of CMA, or component measurement and attestation, or authentication. And we're using SPDM as the specification to go ahead and do this. So the PCI Express endpoint device, or the card, presents the firmware measurement and also presents a certificate chain for the device as well. The PA-RoT will then attest this information. The device will then be verified or authenticated in the platform. If it's not, you need to handle what sort of path you want to take. And if it is authenticated, the host will boot and the device will be a part of the platform. Now, on the right-hand side of this picture, you'll see what we're using for this demo. By all means, this isn't the only way you can do things. In this case, we've got the host, the PA-RoT, and the PCI Express device all communicating independently with each other. You could have the PA-RoT behind a BMC. You could have it in several different places. But as Dong specified, you've got the firmware store of those certificates in the PA-RoT itself. So as the host is coming up in our case here, we have to wait, and in fact, this was one of the things we learned during this exercise as well, for the device to be ready during PCI Express enumeration. Then we had the PA-RoT basically go out, authenticate the device. The host asked the PA-RoT, did you authenticate it? And if it said okay, then it continued on with the normal boot and authentication. Now, the PA-RoT can be used in all sorts of authentication of the platform. It's not only restricted to this. And like I said, it could be in maybe DC-SCM designs. It could be behind the BMC and you're talking to the PA-RoT through the BMC. So many different designs are possible here. Now, this is a kind of a busy slide, but it has the base layout of what happens in an SPDM exchange. By no means is it the full thing, but basically the endpoint device will be asked, what's your version? Supply the version back. It'll supply some capabilities. It negotiates algorithms. These steps are important because you might have an older card working with a newer system or a newer card working with an older system, so that there's some flexibility here on each side of it. But maybe an old card might be rejected because it's not up to snuff on algorithms. Then the measurements are requested. It also provides the certificate back. And this last stage here, we'll talk about it in a second, it's very important on the challenge. Because if you read through this on the right, it really reads that I could just do a replay attack on this. If I'm listening to the bus, I could just say that these are the same things coming back if I've augmented the firmware. But that challenge right there requires that something be signed and sent back. So if you have modified maliciously the firmware, it can't be replayed. It's different every single time. So as we've talked about here, depending upon your design, there might be other players in the middle of the endpoint device and the PRoT. The CPU, for example, maybe also a BMC device. This flexibility is very important because depending upon your designs, it can, you might want to support it in multiple different methods, and the specification is flexible enough to allow these sorts of things. This is our demo setup. It's kind of just expanded out here in this picture. We used an Ampere Ultra platform. There's two Broadcom cards that are in that picture right there as well. One of them has a properly signed firmware with a certificate and will respond to SPDM requests. The other one has an invalid one. And then basically the PA-RoT will come up, communicate with these devices as we talked about during that enumeration process, and inform the host CPU when those authentications are complete. If we look here, this is a bad attestation. So invalid hardware is detected. Now, strictly for demo purposes, we halted the system to show that this device is not working correctly. If you were using this in the real world, you would probably want to recover that firmware, and if you can't recover that firmware because it's something you don't have a backup to, you would then maybe eject the system from the device via shutting down some pins on the bus or shutting down the root port. But basically, at this point, this device cannot be trusted and it should not be used in the platform itself. Similarly, here's a good attestation. And if you come by the booth, we can show you this in more detail. The different images along the top there, you can see the full certificate information. This is really a debug build. In the real world, it would just zoom right by and you wouldn't know that this was happening unless the device did not attest properly and it would be ejected from the platform. Oh, sorry, yes. So why are we talking about this? A lot of people are now building ARM platforms. ARM is becoming much more popular in the CSP space. So you should not try to reinvent the wheel. These ARM platforms are just like x86 when it comes to overall security scope. And also at the same time, even for x86 platforms, you should now be extending security on your platform to all components on the platform. So power supply, plug-in cards, NVDIMM firmware, all firmware that's available on the platform. You should be pushing your vendors for SPDM, capable firmware and other things so that you can make sure they're good. Firmware attacks continue to be on the rise within the National Vulnerability Database. It's one of the easiest sources to check for this information. So you want to be able to authenticate them and revert them back to known good versions when they're available. And the PA-RoT, as an independent device on the platform, provides all of this flexibility at the same time. Policies on handling what happens when a device does not verify correctly. There should be some flexibility here as well. Manufacturers might want to poll their customers, see how they want it to function, maybe give them some abilities to handle it in different ways depending upon their actual design and usage. And as we've talked about again, ARM platforms should utilize all the common security mechanisms that we've built as a community over the last 10 years. If we then move forward. In the call to action, one of the key things to do here is to get involved in the OCP security project. We plugged the link there to it, but this group discusses all these topics and is very key to the overall progression of how we secure these platforms. You should also visit the ARM System Ready OCP Experience Center. It's located on the far end of the hall. You should upgrade your ARM designs with PA-RoT and other security mechanisms. And to join the ARM System Architecture Advisory Council, contact Dong right here. We got his email address in there. And you should join ARM System Ready to make sure your platforms are conforming with all the specifications as well. This is a very good program that allows you to validate that you are in compliance with all of the different specifications that ARM has put forward, from the SBMR, SBMR, and all of the corresponding ones at the same time. Lastly, you can visit both AMI's booth at A33 and ARM's booth at B14 to see these demos, to see how these things function. We've got a number of different hardware root of trust implementations that you can kind of walk through, try them out, and let's continue the conversations. That's all I've got. Thank you. Any questions?
Yeah, I have a question regarding non-volatile memory in NOR flash. Do you see the trend, any trends of that device changing?
I mean, there
means beyond secure boot, right? Do you see attestation being added to it, or the ability to do secure boot validation within the device itself versus?
Let me take this. So yes, yeah, we do see some of the vendors of SPI NOR offering this capability. I would say it's still kind of in its infancy. There's maybe one or two vendors that do offer certain SKUs that do it. But yes, I would say that helps the overall ecosystem to providing maybe a quicker method for doing some of these validations, and it still fits within the overall scope of these things.
Do you see it being adopted?
I haven't seen wide adoption at this time. I've seen some implementations basically take it to production, but I haven't seen wide adoption myself.
Okay, thanks.
Hi. One of your earlier slides showed an illustration where the host wants to challenge a PCI device, and is essentially what I believe is offloading a policy to the PA-RoT. So say, hey, PA-RoT, go challenge this device I'm talking to. I'm curious if you thought of through, I guess, well, there's a couple of man-in-the-middle attacks. I'm interested in your thoughts on specifically man-in-the-middling between the host and the PA-RoT, and then between the host and the PCI device. Like, if the PA-RoT challenges the device which is not the same as the one the host is talking to, is there a concern there?
No, very good question. You're absolutely right to ask something like this. I would say one of the, not necessarily struggles we had with this, but we used a production platform and kind of blue wired this into the platform. So I would take a more secure design if I was to actually do something like this. You're completely right. The host basically reached out, said PA-RoT, attest it. It would be better if we had a complete chain of trust and control flow for these types of things.
Cool. Thank you.
Yep.
I have a question about the policy of when you handle a device that that's invalid. Where do you imagine that policy is going to live in the future? Like, would it be the BIOS, something off the box, the BMC? Just if you have any thoughts.
I would say that's a good question. I would say we probably need to get together as a community to talk about it a little bit. It's an easy way to make a snap decision, but it could be in the BIOS, it could be in the BMC. I would say I want the consumers of these devices to kind of drive this part of the discussion, because we'll make decisions that won't make sense for actual use cases unless we know some of these, but very good question.
Hi, similar in the vein to the other two questions, do you have recommendations on how to quarantine a device until it has passed authentication or attestation, like holding it in reset or must master enable, et cetera?
I would say probably the worst method, the one that we used in the demo, is to hold the system in reset, because then you've just created a brick. But it is a obvious thing when that would occur. I would say bus mastering, shutting down the root port, these sorts of things, outside of if you can recover the device. If you can recover the device, that's by far the best means to do it.
Or rather asking the other way, where what state should the device and the system be in until the verification has happened?
Oh, it should be before bus mastering is enabled on the device, basically. You're doing that verification as that device is being enumerated at that time.
Okay, thank you.
Yep.
Hi, another question. Earlier you mentioned that the ECR has support for redfish, or reporting measurements of a redfish. I'm curious if you looked at the, because redfish also supports direct challenging of SPDM devices and getting the raw measurements. Is that also something supported, or?
I think we actually have an expert in the room for SBMR. So Samer has been working on that quite a bit. I don't recall that we talk about that portion yet, but the ECR you're talking about on the slide was about the PA-RoT support, not the redfish itself. But Samer's here, so.
Yeah, and the redfish portion just follows what's in the DMTF redfish specification, so we're not adding anything new there.
Sure. There are two ways to get measurements of a redfish. One is just give me the measurements that BMC reports, and the other is here's a nonce, and I want you to give me an SPDM stream of bits back.
There is no recommendation for the second method at this time, but if that's a use case people are interested in having, we can definitely consider that. But both are supported.
Okay, thanks.
And it's going to be highly platform dependent as well, platform design dependent.
Gotcha.
Yeah, so the intention of our specifications like SBMR or in the BIOS area SBBR, right, or BBR spec, is to make the servers look like the servers from other architectures, x86, right? So we are leveraging the industry standards as much as possible. So if you have specs from DMTF, if you have specs from the UEFI forum or any other places, if the features are relevant and it's supported on the server space, we would like to do the same.
And I would just like to add that, since we are talking Redfish, that the ARM specifications are actually referring to the OCP Redfish profiles, the basic and the server profile, and requiring compliance with them. One thing that I keep hearing from end users and customers is that those profiles are not sufficient. Redfish is mostly optional. Like, you implement the Redfish specification, you're compliant with the API, but most structures and schema and objects are optional in the implementation. So the way to enforce this is for the industry to agree on additional profiles that are subject domain specific. So if you want security specific profiles that mandate certain behaviors and certain features in Redfish related, for example, for the platform root of trust, this could be something that we collaborate on at the OCP and publish as a compliance profile.
Any other questions? All right. Thank you very much.
Thank you very much.